Hey everybody, this is Mr. Brooks again. So this is wrapping up the very end of Power Series. So we're going to get into Taylor and Maclaurin series. Uh, but before we do that, let's talk about briefly what we just learned about in 11.9 with Power Series representations of functions. So during that section, we were able to say, okay, based upon the structure of the function, so like 1 over 1 minus x, this appears to be the sum of a geometric series. And so from that, we were able to say, okay, if the series converges, then this is the function that's represented by the series. Okay, so the next step we're going to take is in this section, we're going to investigate which functions has a power series representation. And you'll see here that I've labeled PSR. So again, anytime that you see PSR, this is going to talk about a power series representation. And then we're going to talk about how we can find such representations. So the previous section was, okay, this is the function that has its form. But what about functions like e to the x, that no matter how many times we take the derivative or antiderivative, how do we know if it has a power series representation? So that's what we're going to talk about today. So the very first thing that we need to do is let's assume f of x is any function with a power series representation. So we're making that assumption. So that is going to bite us in the butt a little bit later, but for right now, that's what we're going to talk about. So that means f of x has this form of c sub 0 plus c1 times x minus a plus c2 x minus a, the quantity squared, and so forth, where x minus a, the absolute value of it, is less than r. So it has a radius of convergence for that. Okay, if x, or f of x, has a power series representation, we need to find if we can get these c sub n's in terms of f. That way we can represent the function or those coefficients in terms of the original function. So that helps us out in terms of calculations. Okay, and it makes the things a lot more condensed as we go through that. All right, so if f if that's the case, then let's begin with the following. So we need to figure out, oh, what happens to these values? So we have c sub 0 and then c1 times x minus a, and then all of these have a factor of x minus a. Well, if I let x equal a at that very beginning part, that means in the end, what happens to all those terms is, well, all these terms that has a factor of x minus a, they all go to 0 because a minus a is 0. So it doesn't matter what the coefficient is in front. So that would mean in the end is we end up with f of a is equal to c sub 0. All right, well, how can we isolate all the other c sub n's? Or c, let's start off with c sub 1. Just how can we just isolate this guy? Well, let's think about this. If we differentiate, so if we differentiate f, we get the following. So we get f prime is equal to c1 plus 2c2 x minus a, now to the 2 minus 1 power, so that's just the first, plus 3 times c3 x minus a, the quantity squared, and plus so on. And we have said that if a series, if you take the derivative of it, then the radius of convergence stays the same. So we're going to continue that idea. So what we're saying is it has a power series representation. So that means it has a series representation. So when we take the derivative of a series, the radius of convergence stays the same. So that means x minus, so this is again pulling back from our previous knowledge. So x minus a is less than r. All right, well, if we let x equal a again, then f prime of a is equal to c1. All right, well, if we differentiate again, what do we get? Well, f double prime of x is equal to, now c1 is a constant, so that it goes to 0. And then x minus a, the derivative is just going to be just 1. So that means I'm going to get 2c2 plus 2 times, and there's a reason that I'm doing this, 2 times 3 times c3 x minus a plus 3 times 4 times c4 x minus a, the quantity squared, plus so on. Again, its radius of convergence maintains. All right. Well, if we let x equal a again, then f double prime of a is equal to 2c2. All right, let's do that one more time. All right, well, f triple prime of x, and we're going to start realizing a pattern here. So this is why I'm pushing this one more step. So we're going to get 2 times 3 times c3 plus 2 times 3 times 4 c4 x minus a plus 3 times 4 times 5 c5 x minus a, the quantity squared, plus so on. And then we're going to get x minus a is less than r. Again, maintaining that the radius of convergence stays the same for each one of these. Well, if we let x equal a again, we get f triple prime of a is equal to 2 times 3 times c3. Or another way that we could rewrite this, and this is going to lead us into the next bit of this to seeing the pattern, is 3 factorial c3. And notice the next preceding values as we continue to take derivatives. Notice here that this will be 4 factorial. This one here will become 5 factorial and so forth. So the more derivatives that we take, this pattern is going to continue. So if we continue, then we'll find that the nth derivative, f sub n, of a, so if we take the nth derivative, evaluated at a, we're going to get 2 times 3 times 4 times so on, up to, not plus, times n c sub n. Well, this is n factorial c sub n, which means if we solve this, if we solve our c sub n, so remember, that's the thing that we were looking for. If we can find a pattern or isolate all our c subs n's in terms of f of x. Well, if we do this, if we solve this particular thing, we're going to get c sub n is equal to f of n, and that's again n factorial, the nth derivative of a, all divided by n factorial. So remember, we're dealing with a series here of c sub n, and this is just a power series of x minus a to the n, right? This is what we're trying to match here. So notice we have a formula in terms of f, which is great. All right, this is valid. Okay, so we need to worry about the very first term that we dealt with. This is actually valid. Write that a little bit better. For n is equal to 0, if we state 0 factorial is equal to 1. And this is the definition. And f of the 0th derivative is equal to the original function. So that's the two things that we have to hold. And again, this 0 factorial, this is the definition. That will always be the case. So then this way we have no division by 0. And this is, if we don't take a derivative, then we're left with the original function. All right, so this allows us to talk about if a function has a power series representation. Again, I want to emphasize the if part because this is something that we will have to talk about later on. All right, so if f has a power series representation at its center, A, and again, we talked about where these guys are centered at. All right, that is if f of x is equal to the series as n goes from 0 to infinity of c sub n x minus a to the n. and here x minus a, the absolute value of it, is less than r. So again, we're talking about a radius of convergence. Then its coefficients are given as c sub n is equal to f sub n of a divided by n factorial. So this is just what we have proven. Thus, f of x is equal to this power series, which we can then rewrite as the following. As f to the nth derivative evaluated at a, all divided by n factorial, times x minus a to the n. And how its terms would look like is f of a plus f prime of a over 1 factorial, x minus a, plus f double prime of a divided by 2 factorial, x minus a, the quantity squared. And it's going to continue that pattern. And again here, x minus a is less than r. Again, radius of convergence. This here, because of this representation, this is called, or is known as, the Taylor series of a function centered at a. So a Taylor series is just a power series with a very specific form of its coefficients. Here it's the nth derivative evaluated at a divided by n factorial. That's all that is. So the difference, so this is just an extension of power series that we talked about in the previous section. All right. Now, a lot of people have said like, oh man, Maclaurin series were way harder or were easier than Taylor series and so forth. That's kind of the case, but there's a reason for that. So we have a very specific form here. So if our center is 0, then the Taylor series becomes f of x, which is equal to the summation as n goes from 0 to infinity of f sub n evaluated at 0 over n factorial. Again, here our a was 0, x to the n, which is equal to f of 0 plus f prime of 0 divided by 1 factorial x plus f double prime evaluated at 0 divided by 2 factorial x squared plus so on. Here x is less than r. This guy here is called a Maclaurin series. So the only difference between a Taylor series and a Maclaurin series is that a Maclaurin series is a Taylor series centered at 0. That's it. So a Maclaurin series is a Taylor series. It's just here it's a special case when a is equal to 0. So it gets rid of our x minus a. So the nice thing here is that we have x squareds and stuff like that. So really nice powers that we're dealing with for those x's. And that's all it is. So a lot of people get freaked out by it, but a Maclaurin series is just a Taylor series centered at 0. So there's nothing really horrible about them. All right. So we have shown before if, so from this, again, it's a big if here, and I'm going to try to underscore this as possible. So if f can be represented as a power series about some center A, then f is equal to the sum of its Taylor series. All right. So again, if it does have a power series representation, then f is equal to the sum of its Taylor series. So what we're going to do is we're going to look at a very specific example here of looking at e to the x, because this is a nice one. The reason we deal with this one first is because it gets our feet wet. We're not being pushed into the deep end. And also take a moment and see if you can figure out how you can find this Maclaurin series. Again, since I'm calling it a Maclaurin series, this means it's centered at a is equal to 0. So this is a very specific Taylor series. So that's the nice thing, is when I do talk about a Maclaurin series, a is always equal to 0. All right, so if you see that in any other textbook, it's exactly the same. So Maclaurin series, no matter where you're going to look at it, it's center 0. All right, so what we need to do is we need to find the representation of the coefficients. Okay, so all right, well, we're going to start with our function. F of x is equal to e to the x. Well, we know if we're looking at our series, we want to know what the nth derivative, its form is, for this. Well, the nice thing, again, is why we start with this, is no matter how many times we take the derivative, so if we take the first derivative, we're going to get e to the x. If we take the millionth derivative, or the nth derivative, we are going to get e to the x. So this is a very beautiful function in that sense, because every single thing is exactly as the previous. So every single derivative. So therefore, f sub n of 0 is equal to e to the 0, because the nth derivative is e to the x, which is equal to 1. And this is the reason that we like this, is this is for all n. So there's a reason that we go for this at the very beginning. Thus, the Maclaurin series is the following. The series as n goes from 0 to infinity of f to the nth derivative, value is 0. And again, I'm writing the generalized form first, so that way we can see where everything's going. All right, well, f sub n of 0 is 1, so we get 1 over n factorial x to the n. So if we were to write every single term out when we start at 0, well, 0 factorial is 1, so we are going to get the value 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus so on. All right, so this is the Maclaurin series representation of e to the x. We're done. So yeah, you can say, hey, we're done with chapter or 11.10, we're done. Nah, that's not the case. So I also asked, let's find the radius of convergence. All right, recall to find the radius of convergence, the ROC, let a sub n equal, again, x to the n over n factorial, and a sub n plus 1 is equal to x to the n plus 1 divided by n plus 1 factorial. All right, so we're going to apply the limit. So here, remember we used the ratio test. As n approaches infinity, the absolute value of x to the n plus 1 divided by n plus 1 factorial times the reciprocal of this, so it's n factorial divided by x to the n. All right, so here's a couple things that's going to happen for us, is we have an extra copy of x in the numerator, and inside of here, so n plus 1 factorial contains an n factorial. Take, for example, if we had 5 factorial over 6 factorial. If you look at the terms, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. Well, 5 factorial times 6 is 6 factorial. So same thing here, n plus 1 factorial is n factorial times n plus 1, meaning that we're just left with n plus 1 in the denominator. Again, x is a fixed value, so it's going to be some fixed variable. And so as n approaches infinity, it doesn't matter because x is not going to change. The denominator is going to blow up, and so this is going to go to 0, which is less than 1. So, by the ratio test, the series converges, and I'm going to say absolutely in parentheses here. for all values x. Thus, the radius of convergence, r, is equal to infinity, which is great. It means this power series doesn't matter where it's centered at. So that's the cool part that's going to come out of here. And I'm just scrolling here just to see. All right. So therefore, we can conclude rewrite that just a little bit. We can conclude that from our theorem, and this example, that if, again, underscoring this, e to the x has a PSR at a is equal to 0, then e to the x is equal to the series, as n goes from 0 to infinity, of x to the n over n factorial. Okay? Again, there's this big question of if, because that theorem says if it does have a power series, then this is what it's going to look like. All right, so we need to answer the question, well, does it? So how can we determine whether e to the x actually has a PSR? The nice thing is we've kind of figured out, okay, well, its radius convergence is infinity, so that means we should be good, right? Well, that's not really a definitive answer for us. So the big thing comes to this, talking about this is why it's important to know what it means to be a convergent series. So as with any convergent series, f is the limit of the sequence of partial sums. Again, remember what the basic definition of what a series is. A series is just a sequence of partial sums. All right. So this means that sequence, and here we're going to represent it by something else here, t sub x, so I'm talking about the sequence here. Sequence. All right. This is equal to, as I goes from, and remember here I'm going to not go an infinite limit here, or an infinite number of values. So this is just talking about a partial sum, all right, of f sub I of a divided by I factorial x minus a to the I is equal to f of a plus f of a prime over 1 factorial x minus a all the way up to the nth term. Again, this is just a partial sum. All right. Notice here that t sub n is a polynomial of degree n. In fact, we give these guys a specific name. This is what we call the nth degree Taylor polynomial. And it's got a little bit longer name because then it's of f at a. Okay, so when we talk about Taylor polynomials, we're talking about just a partial sum. So this is where we're going to get into some really interesting stuff, especially graphs. So I'm going to try to draw these as best as possible, but then I'm also going to share a link, hopefully on my YouTube, on this YouTube video, that's going to link to the different graphs. If not, use Desmos or use your graphing calculator to graph these next 3 functions, because I want you to see as we increase with the number of terms for the sequence, how this is starting to behave. So for instance, f of x is equal to e to the x. We get the following. I forgot that I left this big space here, so that big space is not supposed to be there. All right. So if we look at the first degree Taylor polynomial, when n is equal to 1, we get the following. And now I remembered why it's there. Okay, sorry. And we just said it was x to the n over n factorial. That's what this guy is. So we get 1 plus x squared over 2 factorial plus so on. All right, so this is going to be the power of the Taylor polynomial, so n is equal to 1. So I'm going to go to when n is equal to 1, so I'm going to get 1 plus x. And then if I look at the second one, then I'm going to get 1 plus x squared over 2. And then the third degree Taylor polynomial, 1 plus x squared over 2 plus x cubed over 3 factorial. Okay, so these are our Taylor polynomials. Okay. All right, just to represent what that means. So this is the really neat thing about this is the way that we can start talking about, well, how do we know if this is a power series representation or not? All right, so we're going to go all the way back to Calc 1, and then we're going to talk about the graphs of these guys. All right, so think about in Calc 1 how we had linearization. And the way I like to describe it is think about being in a hot air balloon. All right, and so we're going to kind of go the reverse course. So think about being high up in the air, or if you've been on top of a mountain or in an airplane or any high building where you can start seeing the curvature of the earth. All right. Well, as you get closer and closer to the earth, all of a sudden that curve starts flattening out to becomes a straight line. And that's a redundant statement, but it becomes a line. So that's what linearization was, is that as you zoom in on a particular spot on any curve, eventually you can represent or approximate on a small interval using a linear equation. So that's the idea here. Well, this works good as an approximation near its center. And for us, since we're dealing with a Maclaurin series, now this again goes for any Taylor series, but since we're dealing specifically with Maclaurin series for e to the x, then here a is equal to 0. If we want to investigate near, let's say x is equal to 2, and we want to look at values near this, we find a Taylor series centered at 2. And that's it. So this is what I'm going to try to draw here. All right. So my first one I'm going to deal with is t of 1. That's 1 plus x. And then I'm going to try and see how this works, because I've not done this one live before. All right. So I'm going to get my lasso tool here, grab this guy, hit the math button, and then you select an option. Here I want to graph 2D, and I'm going to insert this into the page. All right. So this is what this guy looks like. So nothing fancy yet. All right. Well, I'm going to take my second degree one. Okay, let's try that again. Just double checking to make sure everything's all right. All right. And if we went, and we'll go ahead and graph the third one. We can do it off the page. One plus x squared over 2. And then here I'm going to say x cubed over 6, which is 3 factorial. I don't know the length of how well this is going to work, so I'm just going to go ahead and use caution on that part. And let's see here. I'm going to zoom in. There it goes. All right. So that's what this graph looks like. And I'm actually going to redo this one real quick because I want to show the progression. So I'm taking a little bit of time out of this. All right. So notice if we were to graph e to the x in each one of these drawings, all right, e to the x is going to come in through here. So this is the value 1. And we would get something, and I'm just going to horribly draw this as best as I can. So this is e to the x, and this is our t1. And if I come back through here, notice that the graph is starting to actually get close to that representation. So this is e to the x, and this is t2. And if I come over here, then we're starting to pick up more of that curvature of e to the x. So notice it kind of makes sense the closer and closer, or the more terms that we have of the Taylor polynomial, eventually these guys are starting to behave like e to the x. Well, in fact, if we try to write one of these out, and I'm going to go out big here just to see, one, I'm pushing the limits of this as well. And we're not going to go to 10. 10's too big. I kind of chickened out. We'll go x to the 6th. So we'll go to the 6th degree Taylor polynomial. See what it looks like. And we'll go 7 because I like that, what that's going to do. All right, we're going to see what this is going to do for us. It might not like this, so we're about to find out. Yep, it does not want to graph it. All right. Well, eventually what you would start seeing is that these two functions would become closer and closer in their uh, respective shape, as you will. And so as we increase the number of terms, this shape is going to be closer and closer to e to the x. So this is, we're using these guys as approximation tools then. All right. So the next thing is this leads us into what we call Taylor's inequality, which is going to be coming up here in just a second. But before that, let's talk about these graphs again. As n approaches infinity, then we can start seeing that the nth degree Taylor polynomial, or the partial sum, is approaching e to the x. In general, if f of x is the sum of its Taylor series, if f of x is equal to the limit as n approaches infinity of t sub n of x. Meaning, as n approaches infinity, the more terms that we get, the closer and closer we are getting to this function. All right, and that's what a series is. A power series representation is the sequence of partial sums. So if this partial sums approaches f of x, then it has a power series representation. So if we let, and now we're going to talk about, okay, well, how do we know how close we are to this representation? Well, if we let r sub n of x, all right, well, great, we're introducing a new term. That's okay. Here, I'm going to say it's f of x minus the Taylor polynomial. So this is the remainder, okay? Or f of x is equal to the Taylor polynomial plus the remainder. All right. Again, here Rn of x is the remainder of the Taylor series. So if we subtracted the two, that's what we're going to get. Okay. All right. So what that does is if we can show, that the limit as n approaches infinity of r sub n of x, if we can show that that remainder is equal to 0, then the limit as n approaches infinity of the Taylor polynomial is equal to the limit. And here this is just doing some algebraic manipulation here. Again, here Taylor polynomial, if we rewrote this again, is equal to f of x minus the remainder, which is just, again, the remainder is f of x minus the Taylor polynomial. So this is just some algebraic manipulation. If I split this up as n approaches infinity of f of x, well, actually, in fact, we already know what that is since this is not affected by n. This would be f of x minus the limit as n approaches infinity of r sub n of x. This is what we want to show. If we can show that this remainder goes to 0, then our Taylor polynomial is approaching the function. Therefore, the function has a power series representation. But let's think about that for a second. We have to show a function is approaching 0, which means that's some fun math to go through. So this is where our theorem is coming into play. So we've talked about this theorem in general. So if we can show that this remainder goes to 0, then we're golden. All right. So if f of x is equal to the Taylor polynomial minus its remainder, sorry, plus its remainder, plus, make sure that's plus, where t sub n is the nth degree Taylor polynomial of f at a, and the limit of the remainder is equal to 0, And notice here we're talking about the radius of convergence. At some point, we might not be converging for all real numbers. That's okay. All right. Then f is equal to its Taylor series on that interval of convergence, or that radius of convergence. All right. So if we can show that, then and the limit is equal to 0, then we can say f has a power series representation equal to its Taylor series. And that's it. I say that's it, but then how do we get to that r's, the remainder is going to 0? This is where Taylor's inequality is coming to play. So these two are going to go in pairs. So if, let's do this with a different color. The absolute value of the nth plus 1 derivative of x is less than or equal to some big number m. Now this is saying the size of f of x. So for any value of x, if we can let that value be less than or equal to some big number, so we're putting a upper bound to it, okay, or bounded above. For x minus a is less than or equal to d, so this is the radius of convergence. Okay, then the remainder, r sub n of x, of the Taylor series satisfies the following inequality. The remainder is less than or equal to big M over n plus 1 factorial x minus a to the n plus 1. Notice this looks very similar to the alternating series estimation theorem, where we talked about the remainder of a series, s minus s of n, is less than the nth plus 1 term. That's what we're associating with this. All right, so that's that similar principle. For x minus a is less than or equal to d. All right, so again, Taylor's inequality says that if this is true, if we can set this less than some big number m, then the Taylor series satisfies the inequality. We want to satisfy that. So this means we want to be within some error, if we will. All right. So let's show how we're going to prove that for e to the x. Okay, and then we're going to use a similar walkthrough for sine of x and cosine of x. Okay, so prove e to the x is equal to the sum of the Maclaurin series. All right, so we've already found its Maclaurin series. And again, just as a reminder, this is the Maclaurin series, and we want to show, is this true? Is this equal to e to the x? All right. Again, things that we know, because we're going to need these here in just a second. We need f of x, we know that is equal to e to the x, and the nth plus 1 term, because we're going to pop up Taylor's inequality here in just a second. So when we take the nth derivative, or the nth plus 1 derivative, we're still going to get e to the x out. And this is true for all n. All right. So now we're going to incorporate the inequality part. All right. For 0 is less than x, which is less than d. Now, okay, again, I'm saying here that on some interval of x, we can say the following is true. We can say the absolute value of the nth plus 1 derivative of x, which we stated is e to the x, is always going to be less than or equal to e to the d. Okay, so what I'm doing here is I've said on this interval from 0 to d, so from our center out, so this distance out, the biggest that e to the x is ever going to become on this interval is d. So e to the d, and this is why I'm writing this in red, this is a note to ourselves. This is our big M. Okay, we need to establish a number that this is bigger than. So we're going to let a equal 0 and m equal e to the d. Again, since the reason a is equal to 0 is because we're dealing with the Maclaurin series, and that's why we're doing that. So here's Taylor's inequality. So now applying Taylor's inequality. All right. So I'm going to go back to my green here because that's how I started it. So the red is just a note to ourselves. All right. Just rewriting what Taylor's inequality was. And then I'm going to fill in the pieces. All right. So again, this is just reiterating Taylor's inequality. All right. So let's fill in the blanks. R sub n of x, we don't know yet because that's what we're going to be dealing with, is less than or equal to, well, we just said on the interval from 0 to d, e to the d is our big M. All right. The nth plus 1 factorial times x, because a was equal to 0, to the n plus 1 term, for absolute value of x is less than or equal to d. All right. Now, well, we've got this nice, pretty established formula, but what are we trying to do? Think about back to our theorem. If we can show that this is going to go to 0, that r sub n of x is equal to 0, or is forced to go to 0, then f is equal to its Taylor series representation. All right, so keep that in mind. So do we have a way to force r sub n of x to go to 0? Well, if that's the case, that means it's an absolute value, right? So it's not going to go negative. So that means we can put a lower bound on this, actually. So I can say 0 is less than or equal to the absolute value of r sub n of x, which is less than or equal to e to the d over n plus 1 factorial, absolute value of x, n plus 1. All right, and again, for absolute value of x is less than or equal to d. All right, so if we can show this goes to 0, as n approaches infinity, then it forces r of n of x to approach 0 as well, right? So that means let's apply the squeeze theorem. Okay, so I'm going to take the limit as n approaches infinity of 0, and that goes to 0. So this is just again establishing that first term. Here n approaches infinity of e to the d over n plus 1, the factorial, times absolute value of x, n plus 1. All right, well, another way to state this is e to the d times the limit as n approaches infinity of absolute value of x to the n plus 1 over n plus 1 factorial. Now we are going to cheat here just a little bit. We have established in the past before that the limit as n approaches infinity of x to the n over n factorial is equal to 0, meaning the factorial function grows faster than the exponential. And we have seen that in the past. And this again is for all x. Okay? So, if that's the case, then if we raise this to the nth plus 1 term, that means this is going to go to 0. We get e to the d times 0, which e to the d is some value. Okay? D is any value. This is equal to 0. So by the squeeze theorem, the limit as n approaches infinity of r of n of x has to equal 0 for all x. Well, what does that mean? Well, okay, so we just said that that the limit as n approaches infinity of the remainder goes to 0 for any x value. Well, going back up to our theorem, what does that mean? Well, our theorem says if we establish f of x is equal to the Taylor polynomial plus its remainder, where t sub n is the nth degree Taylor polynomial, and as n approaches infinity, this goes to 0. So we just established this part. And we established the nth Taylor polynomial, then f is equal to its Taylor series. Therefore, e to x is equal to, or is the sum of its Maclaurin series. So, e to x is equal to the series as n goes from 0 to infinity of x to the n over n factorial for all x, meaning it's equal to 1 plus 1 over x plus x squared over 2 plus x cubed over 3 factorial plus so on. Which means if I plug in for any value of x, I can find out an approximate value for the Maclaurin series, or find out for any value of x. So this means the series, so an example of applying this, as n goes from 0 to infinity, of let's say let x equal 1. 1 over n factorial is equal to e to the first, which is just the value e. Or another example, if I let x equal 2, that means we have 2 to the n over n factorial is equal to this very specific value of e squared. That's the really cool thing with this. All right, which then, notice that this is a good application of what happens for things that we do not know how to take or have a particular elementary antiderivative. So e to the x squared. We're going to soon see how we can modify these, and then we know if we have a series, we can take the derivative or antiderivative of those. So if we can rewrite e to the x squared as a power series, then we can do a term-by-term derivative or antiderivative to solve them. So that's the cool thing. This is the real big benefit of these. All right, so now that we've established that, let's talk about sine of x. All right, sine of x is just a little bit different beast, but it still works out really nice. And I want to prove, so this is going to have all the parts to it. All right, well, we need to establish what happens to the nth derivative. Well, f of x is equal to sine of x. F prime of x is equal to cosine. F double prime is equal to negative sine f triple prime is equal to negative cosine and f to the fourth derivative is equal to sine of x. And it's going to repeat that pattern every single force. So if we let x equals 0 or let a equals 0, then we're going to get 0, 1, 0, negative 1, 0. All right. So if we were to look at this, this means this is equal to f of 0 plus f prime of 0 divided by 1 factorial x. Again, dealing with Maclaurin series, so a is equal to 0, plus f double prime of 0 divided by 2 factorial x squared, plus so on. Well, this is equal to f of 0. I'm going to get 0 out, okay, plus x, plus 0, minus x cubed over 3 factorial, plus 0, plus x to the 5th over 5 factorial, plus 0, minus x to the 7th over 7 factorial, so forth. Notice that we can reduce this down. So look what this becomes. This is alternating series. And we can rewrite this if we look at the terms. Since we know it's alternating, that's negative 1 to the n. So there's our alternating piece. X to the 2n plus 1 divided by 2n plus 1 factorial. All right, so this is our Maclaurin series. Now we need to show. So this is where Taylor's inequality is going to come into play. So Taylor's inequality. All right. Well, since the nth plus 1 derivative of f of x is either equal to plus or minus sine of x or plus or minus cosine of x, we know that the nth plus 1 derivative of x is always going to be less than or equal to 1 for all x. Again, we're talking about the size of the function. So what's the biggest number that we're ever going to get out of this? Well, sine and cosine both fluctuate between negative 1 and 1. So that means if we take the absolute value of it, that means it's going to be always less than or equal to 1, no matter what value of x that we throw in there. So this means we have our big M. And the nice thing is this is for all x. All right? So let big M equal 1. So the remainder, again, just rewriting this so that way you can see where it comes from and where to plug in these pieces. All right? Well, this is equal to 1 divided by n plus 1 factorial times the absolute value of x to the n plus 1. All right, just like before, if we can force this to go to 0, 0 is less than or equal to r sub n of x, which is less than or equal to 1, or absolute value of x, to n plus 1, divided by n plus 1 factorial. All right, so we take the limit as n approaches infinity. The absolute value of x to the n plus 1 divided by n plus 1 factorial. And this guy we've already established before that he goes to 0. So thus, by the squeeze theorem, the limit as n approaches infinity of the absolute value of r sub n of x is also equal to 0, which establishes our next point. Therefore, sine of x is equal to the sum of its Maclaurin series and therefore sine of x can be rewritten as a power series. Which is equal to the series as n goes from 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And this is true for all x. That's the cool thing. So again, by showing that the remainder goes to 0, we are proving the fact that this series is equal to sine of x. That's what we're doing. All right. So take a moment and see what you can do for cosine. Notice I didn't leave a lot of space here. There's a purpose for that. All right. So pause the video and try it out. All right. So now we could go through the same exact process. All right. But there's something that we're going to do here. There's a loophole that we have. It's easier just to use derivatives. So we're going to apply Theorem 11.9 All right, this is coming from, again, the previous section. So where we said that a series converges or convergent series is derivative or antiderivative. That's where this is coming from. All right, so cosine of x is equal to the derivative of sine of x, right? Which is equal to the derivative of this term-by-term approximation or power series representation of sine. So why work harder when you can work smarter here? Okay, so when we take the derivative of this term-by-term process, we're going to get 1 minus, well, if take the derivative of x cubed, that's 3x squared. And the 3's will cancel, so I'm left with x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so forth, which means we can rewrite this as n goes from 0 to infinity of -1 to the n of x to the 2n over 2n factorial. This is true for all x. Well, why don't I have to prove this just like before? Well, think about this. We already know that sine of x converges for all real numbers of x. So since sine of x converges for all x, then cosine of x converges for all x. So this is actually establishing using Theorem 11.9, where we said if we could take the derivative or antiderivative of a series, then it also converges for the same radius of convergence. And since we're dealing with an infinite radius, then cosine is going to converge for all values of x as well. So that's the cool thing. We are just simply, we're not cheating. We're using the properties of these guys. All right. So I've got a couple more for you. And then we're also going to look at a new series as well called the binomial series. But I want to establish these guys. So find the Maclaurin series for x cosine of x. This is something that we could take an antiderivative for, but it's okay. So, and again, the motivation behind these is eventually for things that we are not been able to take a derivative or an antiderivative of, we can use power series to help us. So this is kind of a motivational piece. Well, x cosine of x can be written as the following. X times the series as n goes from 0 to infinity of -1 to the n x to the 2n over 2n factorial. Okay, remember here, x is a specific value. Okay, so it's treated as a constant. And again, since n is our index, if I multiply by x in here, I'm not changing anything. It's not a value by n, so it's the same thing as if I multiply by 3. So when I do that, I just get the series of -1 to the n x to the 2n plus 1, because I have an extra copy of x, divided by 2n factorial. And that's it. That's all you have to do. So once you start establishing these base functions, that means products and stuff like that are going to be really easy to establish. Or even, our next problem, what if we had a composite function of sine of x squared? Now let's think about this. If I had the sine of x squared, that's going to be impossible or really difficult to deal with when talking about its antiderivative. However, there's things that we know. We can say let g of x equal sine of x. Thus, this is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial and whatnot. Now, because sine of x squared is equal to g of x squared, we can substitute x squared for x into our series. So sine of x squared is equal to g of x squared, which is equal to, well, for every x I see, I'm going to replace it with x squared. So I'm going to get x squared minus x squared to the 3rd power, which is x to the 6th divided by 3 factorial, plus x squared to the 5th, which is x to the 10th over 5 factorial, minus x to the 14th over 7 factorial, plus so on. All right, well, that's the same thing as if I replaced x in its power series representation, as n goes from 0 to infinity of -1 to the n of x to the 2n plus 1, all divided by 2n plus 1 factorial, which is equal to the series as n goes from 0 to infinity of -1 to the n x to the 4n plus 2 over 2n plus 1 factorial. And that's how we can operate those. Now, we could take the derivative and notice every single time that we take the, we could establish all these derivatives and come up with the new Maclaurin series that way. So there's a couple ways that we could do that. Or we could go for the shortcut. All right, and then again, it's just establishing, hey, this is just x again is a fixed value that we're dealing with. All right. So the binomial series is a little bit different. So this one is for some value k, and we're going to determine its radius of convergence. All right. The biggest thing here is we are going to assume k is a positive integer. And k is not equal to 0. Okay? So f of x is equal to 1 plus x to the k power. So that means f prime of x is equal to k times 1 plus x to the k minus 1 power. F double prime of x is equal to k times k minus 1 times 1 plus x to the k minus 2. All right, and if we take the third derivative, again, pulling these extra copies of k down, k minus 2 and 1 plus x to the k minus 3, and so forth, we start realizing how we're building our coefficients here. So the nth derivative of x, or of the function, is equal to, and again, we're talking about a finite number of terms here. So it's a positive integer. That's the one big thing. All right. That means we're going to get k times k minus 1 times k minus 2 and so forth times k minus n plus 1. All right, because we're taking one bigger away from it, times 1 plus x to the k minus n. All right, again, look at this. We took the third derivative, so k minus 3, k minus n, and we get k minus 2, so k minus n plus 1. All right, well, we're finding the Maclaurin series. So f of 0, when we plug 0 in for x, we're just going to get 1 out. When we get the first derivative, we're going to get k out. Second derivative, we're going to get k times k minus 1. Third derivative, we're going to get k times k minus 1 times k minus 2. So forth, the nth derivative evaluated at 0 is k times k minus 1, so forth, times k minus n plus 1. All right, which gives us the following. One plus kx plus k times k minus 1 divided by 2, x squared, plus so forth up to k times k minus 1 times k minus n plus 1, all divided by n factorial x to the n, which is equal to, series as n goes from 0 to infinity, of k times k minus 1 all the way up to k minus n plus 1 over n factorial x to the n. All right, so we know what this guy looks like. So let's find its radius of convergence, where this guy is going to converge at. So applying the ratio test, we're going to get the limit as n approaches infinity. This is going to be a fun one. All right, so this is our nth plus 1 term. So I brought down the next power, which is k to minus n. And then the reciprocal of our nth, or of our a sub n. All right. Notice a lot of things are going to cancel for us. So all this mess is going to cancel, leaving us with just the following bits of k minus n divided by n plus 1 times x. Well, that means here k is a fixed value, n is the only thing that's changing. And if we divide all the way through by n, we're going to get k over n minus 1 divided by 1 plus 1 over n x, which is just going to give us the absolute value of x in the end. So, since this is the ratio test, this converges for all values less than x. So the binomial series converges if absolute value of x is always less than 1. All right. So that's just another series to deal with, just giving some more information out there. So this leads us into our list of Maclaurin series and the radius of convergence. So I'm going to bring in some stuff that we talked about in the previous section because now we can actually establish those guys as Maclaurin series. So our first one we're going to deal with is 1 over 1 minus x. This was equal to the series as n goes from 0 to infinity of x to the n. We established that its radius of convergence, r, is equal to 1. Then we had e to the x, which we just established today. N goes from 0 to infinity of x to the n over n factorial. Here we have found out that its radius of convergence is infinity. Sine of x, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Radius of convergence is infinity. Cosine of x. These guys are very similar to each other. And they should be because we know graphically that these two are just a shift of each other. So they should be similar in their nature. Radius convergence is also infinity. Arctangent, which we talked about last class. The series as n goes from 1, 0 to infinity of negative 1 to the n, x to the 2n plus 1 all over 2n plus 1. Its radius of convergence is equal to 1 though. That's something that you have to be careful about for this. It's very similar to sine, except it does not have a factorial in the denominator, and also its radius of convergence is 1. Another one that we established is the natural log of 1 plus x, which is equal to the series as n goes from 0 to infinity. Actually, this one starts at 1. Of negative 1 to the n minus 1 x to the n over n. And its radius of convergence is also equal to 1. And lastly, our binomial series, which we just established. Whose radius of convergence is also equal to 1. So the reason that I'm using these is to one, establish a list. One, we've already proven these. And two, if we can use these to manipulate, or where we saw a sine of x squared, where we can use a composite function to build a series, and we've already proven the base series, if you will, then we can use these guys to our advantage. So this is very important to have. All right, so now that we've established all of this, how can we use it? Well, we can finally use it to find things of this nature, of e to the x squared. This is something that does not have a elementary antiderivative, so there's issues with it. All right, so what we need is a way to deal with him. Well, this is where power series representation is so important. This is why chapter 11 was so important, establishing everything that we needed. All right, so we know e to the x is equal to this 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth. All right. And here I'm actually going to go one step further and make this, there's an error with this one. So I'm actually scratching this out. We're going to go with just a modified version. The reason I'm going with this one is because it's going to be a lot more easier to deal with, and there's something that we're going to pull in from here. All right. So e to the negative x squared is equal to, so for every x that we see, we're going to replace it with negative x squared. So we're going to get 1 minus x squared over 1 factorial plus x to the 4th over 2 factorial. Now you're going to see why I did this. X to the 6th over 3 factorial plus x to the 8th over 4 factorial minus and so forth. Notice what we're doing. We're establishing an alternating series. This is very important for us. Now let's integrate from 0 to 1 of e to the negative x squared dx. Well, that's the integral of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so forth. Well, this becomes x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial, and so forth. And we're going to establish that from 0 to 1. Well, if we look at these, if I plug 0 in for all this, then it all goes to 0. And so I'm left with 1 minus 1/3 plus 1/10 minus 1/42 plus 1 over 216 minus 1 over 1320 plus so on. Well, if I start looking at these values, so I wanted to be with an error of 1/10 or 1/100th. So if we look at this, this is 0.1. This is 0.023, so that doesn't get us in our error. This is 0.0046, and this is even smaller. So these guys are not going to affect the second decimal place. So therefore, using the first four terms, we can approximate this to be 0.74. And just to give this value, 0.0757, because I've already got it written down. So just using the first four terms of this series, we're able to establish the area underneath the curve of something that we would not have been able to find the antiderivative of. So this is why this particular section is so important for mathematics in general, is because we can use these as approximation tools, which is awesome. And so that's where section 1111 is going to come into play, is establishing these for what applications we can talk about, what accuracies we can use this for. And so you'll see my notes are already pre-written, so I will be posting a video tomorrow going over 1111, which is just, again, talking about something that we've establishing a usage out of this. And so the main goal we have now established is we can use these as approximation tools with a high accuracy if we wanted to. So this is the beauty of this section, is because this is the culmination of everything that we've wanted to talk about, because there's things that we normally would not be able to find the antiderivative of, and now we can establish something that gives us an awesome approximation for. So that's it for 1110, and we'll have just one more video and we're done for the semester. Y'all have a wonderful day.